let's continue. We'll finish the introduction part of the course, which is the outline of this class. And last time we mentioned that we will first give you a very brief introduction to the solid state 1, and then we'll introduce fermionic or electron systems for ordinary metals, but including Coulomb interactions. And then we will introduce this phonons, lattice vibrations, which is bosonic excitations. And after that, we will introduce magnetism, which is the magnetic properties of solids. And then we will give you some review of all these magnetic properties, including paramagnetic, ferromagnetic, antiferromagnetic, and diamagnetic. So I will give you some overview of this phenomenology of all these different magnetic properties of solids, and then we try to describe the low energy excitation of those magnetic materials. And we will use a semi-classical picture, which we call the spin wave analysis. And then we introduce second quantization method, derive such a spin wave theory, and in particular, we focus on another important bosonic excitations called magnon excitations, which are spin wave excitations of these magnetic materials at low temperatures, and the energy of this magnon are quantized energy, and which is again another example of the quasi-particle in the bosonic sector. After this, we will talk about electron-phonon coupling. Again, so we'll finish introducing this fermionic or electronic properties of metals, and then phonons, and then spin wave magnons. After that, I will use the very general Hamiltonian to describe our solid state systems, which consists of ions and electrons, and they are coupled by Coulomb interactions, also some sort of a spin-spin interactions. So electrons were coupled to the lattice vibration. So we will study that such a coupling between electrons and phonons. And this will lead to very many interesting new phenomena, which you may or may not know. For example, this will lead to so-called Coulomb anomaly and some modifications of phonon energies and also electron energies. So the electron-phonon coupling will modify not only the electronic part of the energy, but also the phonon part of the energy. And there will be 2kF scattering between electron and phonons at the edge of this Fermi surface, and we will discuss in that part. But more importantly, will lead to some so-called polaron and electron mass renormalization. So the polarons is again another fancy name in the valence solid state, which means that the electrons can actually carry a very heavy bag because the electrons couple to phonon, and those phonon will actually come into drag this electron, and so the electrons will become heavier, and so they cannot move very as fast as they can. So electrons get fat and fatter, so which means that the effective electron mass is getting bigger and heavier, so-called electron mass renormalization due to the electron-phonon coupling. So we will discuss this kind of a mass enhancement in this electron-phonon coupled system. As all these phenomena have been observed in experiments. So everything that I tell you here are real phenomena. Okay? So, but how to really understand those phenomena is the key of this course. Okay? So we need to have a very systematic way to understand all these well-known phenomena. Okay? So these phenomena are not new. Look at the textbooks and they're all there. But the problem is how to understand this correctly. So that's the non-trivial task. So the most important effect of electron-phonon coupling is to introduce the attraction between electrons. So which is somewhat counterintuitive, strange, because we know from our childhood that the two electrons can only repel each other. right? And how come two electrons are attracted to each other? Okay, but again, this attraction between two electrons is the hallmark of electron-phonon coupling, which we will introduce at this part, that two electrons can attract to each other, and they can actually fight against the Coulomb repulsion. And the consequence of this attraction between two electrons lead to the Cooper pairs, which is the electron-electron pair. So two electrons can form a pair, which we'll call this Cooper pair, and that Cooper pair becomes a boson, and when boson gets condensed, it superconducts, which means that this will lead to the superconductivity for ordinary metals. So all metals will become superconductor as long as temperature is low enough. And the reason why these metals become a superconductor is because of these Cooper pairs formed by two electrons. And the reason why the two electrons form Cooper pairs is because the attraction between two electrons. The reason why the two electrons become attraction because of electron-phonon coupling. Okay, so the logic is actually a cascade coming from electrons and phonons and the coupling between them. And coming from this electron-phonon coupling, we could derive this attraction between two electrons, which lead to this very non-trivial phenomena called the superconductor, which means that there is no dissipation, no resistivity for these superconductors as long as the temperature approaches zero. So this phenomena has been observed, say, over 100 years. So in 1911 or 1912, I think this is the same age as ROC. So in Netherlands, in Leiden University, experimentalists called Ernst discovered such a phenomena that in mercury, if he keep reducing the temperature, I don't know, a couple of Kelvin, a single digit Kelvin, less than 10. And the electrical resistivity of the mercury drops to zero. So there's no resistance. And it's like a super flow, a super current. And this is a discovery of a superconductor for mercury for the first time. So in this part, we will study how come the resistivity of ordinary metal could drop to zero below a certain critical temperature. I'm telling you here that the reason is because of the attraction, and the attraction comes from the electron-phonon coupling. So this is something I'm sure that you don't know or you don't understand at this point, but you will understand by the end of this semester. Okay? So this, strange terms like a superconductor, a Coulomb anomaly, and polaron, and magnon, and they sound very weird terms. You don't know what they are, but you will know what they are. You will understand what they mean. Okay? So this is what you will learn from this class. All this fancy physics terms at low temperatures in solid states, and you will understand what they are as long as you know the second quantization approach. And this is the the final part, BCS, theory of superconductivity. So thanks to the three great theorists, Bardeen, Schrieffer, and Cooper, in the 1950s, they tried to use a simple mean field theory to describe such superconductivity in ordinary metals. And they got the Nobel Prize. I don't know when. You could check Google. So we call this BCS theory. So it's basically it's based on this Cooper pairing of two electrons that is coming from electron-phonon coupling. So we will learn this theory at the very end of our semester so that you get complete pictures of most important ingredient in the solid state, meaning metals, insulators, magnetic materials, and phonons, electron phonons, and superconductors in ordinary metals. So those phenomena that you are familiar with or not so familiar in your introductory level of a solid state will be introduced in this course with the help of a second quantization approach. So that's the end of the outline of this course, and you will give a broad idea what you will learn and what kind of phenomena that you will study, and these are the phenomenology and the approach that we'll take for this course. So all the phenomenology sounds familiar to you, but you have not understood them. But don't get frustrated, you will understand those things as long as you study hard and you really understand the second quantization approach. Okay, so I hope by the end of the semester you will get a very deep understanding of this elementary solid-state physics, but using this very frontiered technology called the second quantization approach. So that after this course, you could very proudly announce that I understand solid-state physics. It's not just a superficial understanding, but a deep understanding. And the reason why we have a deep understanding is because we can count the quasi-particle by second quantizing the Hamiltonian of our system. So let's move on to chapter 0, which is a very brief review of your solid state 1, and which is a very simple Hamiltonian, but is easier said than done. So the universe of the solid state system is made of the Hamiltonian, which is a quantum mechanical operator describing the total energy of your system, right? The Hamiltonian. So we know that this solid state material consists of electrons and ions and all sort of interactions among them on a periodic lattice. So the unique features of the solid state system is that all these atoms and ions are sitting in a periodic way. Okay, so they are very ordered in space. They are not like a liquid or a gas that the atoms are not crystallized. Instead, it's crystallized. So all the dots represent the ions, okay? And they're sitting in a very ordered fashion like this. There are much more electrons and ions surrounding this ion core. Those electrons, sometimes can actually hop from one side to another, okay, like this, and they may form a metal or an insulator or a semiconductor or semi-metal and so on. But this is basically what we have. Okay, a bunch of ions sitting in an ordered array in three-dimensional space and surrounded by millions of electrons, and the number of electrons is of the order of 10 to the 23rd, that many, and they satisfy in principle the Schrödinger equation, okay, in quantum mechanics, because they are all quantum particles and they form a lattice. Okay, so all this very strange or interesting phenomena that we can see from the solid state basically could be described by this Hamiltonian. It's made of the ion part, the electron part, and electron-ion coupled part of the Hamiltonian, and of course there may be some spin-spin interactions and also external field. So let's just decouple all these pieces of this full Hamiltonian. So the ion part of the Hamiltonian consists of this kinetic energy plus the ion-ion potential. Okay, so suppose this is, say, ion J, X ion J. So I suppose you already learned part of the quantum mechanics, right? So you know this kinetic energy operator in quantum mechanics, and also potential energy is again, in principle, a quantum mechanical operator. Okay, so the ion part of the Hamiltonian consists of the kinetic energy part, p squared over 2m, where m is the ion mass, and the potential energy, okay, which is the say the ion potential energy. This ion potential energy, which may show attraction when they are far away, but there is equilibrium position, which stabilizes lattice structure at a particular distance. Then if you actually push them closer and closer, these ions actually get repulsive very strongly, and so their potential becomes almost infinity when they are really touch each other, okay, because of the, again, repulsive Coulomb interactions. And all these ions carry positive charge, and of course electrons carry negative charge. And there is a charge neutrality condition that if you sum over all this positive charge and negative charge, usually you get 0, okay, because there's no extra charge for ordinary charge neutral materials. So that's the ion part of the Hamiltonian, and of course there's an electron part of a Hamiltonian. Again, we use the little lowercase momentum operator to denote the momentum for electrons, and this is the kinetic energy. Of course, electron are repulsive to each other, as we know, following the Coulomb potential, where we know that the two electrons here and there they interact by this repulsive Coulomb potential between two electrons. So that's well known. And we have electron ion potential, which is again that we just wrote down over there, the electron phonon. We'll see that this comes from this electron ion potential. So there is an electron ion attraction because the ions carry positive charge and electron negative charge. So these two different charge particles attract to each other. So you get attraction between electron and ion. And there may be in magnetic materials some spin-spin interactions between the lattice side I and the spin on side I and side J. And of course, we can have external fields, such electric field or magnetic fields, which are coupled to the charge of your solid state material. So this is the universe of our solid state, and all these interesting phenomena can be derived from such a naive-looking Hamiltonian. So suppose that we can invent a supercomputer which has the capability to solve the Schrödinger equation for that many electron ions, and we are done. So everything that we introduce over there could be understood. Suppose we are able to solve the Schrödinger equation for that Hamiltonian consisting of that many electron ions. But in practice, it is impossible. So it is impossible to solve the Schrödinger equation for that many electrons described by this simple, naive-looking Hamiltonian. So this Hamiltonian is easier said than done. It is relatively easier to write down the Hamiltonian of a solid state, but it is extremely hard to solve them, the Hamiltonian, okay, and find the eigenvalues, and find all these excited states, and so on and so forth. So it is almost impossible, mission impossible. But nevertheless, we should find a clever way to circumvent such a difficulty, and this is the place where we introduce a second quantization approach. Okay, so let's take a short break. When we come back, we will describe how, in principle, we could solve for this many-body quantum system in solid state. So let's talk about the quantum statistics or quantum mechanics. So I will make connections of this Hamiltonian and all these topics that I just listed over there, the outlined. So if we look at the electronic part of the Hamiltonian that I mark here, and this is the subject of the first few chapters, which is the low temperature properties of metals. Okay, so metals consist of many mobile electrons, but they are interacted by Coulomb repulsion, right? So free electron gas plus Coulomb interactions, okay, is what we are going to describe in the first 3 chapters. It's not just ordinary metals, but free electron plus Coulomb. All sort of this, the screening of a Coulomb potential and dielectric properties of solids and so on and so forth will be addressed by looking at this piece of Hamiltonian. And if we look at the ion part of the Hamiltonian only, okay, suppose that we pretend there's no other terms in the Hamiltonian, but just look at the ion part of the Hamiltonian, which is made of what's the ion kinetic energy plus the ion potential energy. And this part of the Hamiltonian is what we will study later in the chapter that we describe the lattice vibration or phonon. Okay, so by studying this lattice vibration of ions, and we could single out this part of the Hamiltonian, and we could second quantize this piece of Hamiltonian, and we get phonon modes and lattice vibration in the second quantized form. And suppose we encircle this electronic part, kinetic energy, and electron ion part of this Hamiltonian, then we could address electron-phonon coupling. Of course, there's a phonon part. And this is, again, the part 3 of our topics. And we could actually encircle this ion part of the Hamiltonian and kinetic energy of the free electrons and plus electron ion potential. And by analyzing all these pieces, we can understand and derive the electron-phonon coupling. And suppose we only study the spin-spin interactions of magnetic materials, and this will lead to this spin wave of magnetic or magnetism of magnetic materials, okay, such as spin waves, magnons, and so on. So you see, this naive looking Hamiltonian actually is everything. It contains everything in this course. It's just different pieces of the full Hamiltonian. Okay, so if we look at part of the Hamiltonian and we understand part of the phenomena, and if we combine this and that, we get a new phenomena. Of course, the superconductivity could be derived from electron-phonon coupling, so that's the final part of the course. So you can see that the full Hamiltonian is our universe of a solid state, and suppose we can really solve this Schrödinger equation for that many electrons described by the Hamiltonian, and we are done. So suppose we could do that, and what we should be doing is to solve this Hamiltonian at 0 temperature, and by solving for this time-independent Schrödinger equations, right, Schrödinger wave functions, for as many electrons and as many ions as they possibly can include. Okay, so this I runs from 1 to say 10 to the 23rd. Okay, so this is a heavy duty because in general, it's not possible to get this solution for that many electron ions. But suppose we are able to do so. What is the next thing? Again, we can actually try to solve the time-dependent Schrödinger wave functions, again, for that many electrons ions, and we find the eigenvalues and eigen wave functions, right? Okay, for that many electrons. And what we will do next is to increase the temperature from 0 to the finite temperature, and we employ this quantum statistical mechanics, because this is the many-body system, and we have many eigenvalues and eigenfunctions, and they should satisfy this quantum statistical mechanics, right? So the way that we calculate this expectation value of any physical observables is to calculate this density matrix. Rho, which is defined as one of the partition function, e to the minus beta h, where this partition function is a central quantity in quantum statistical mechanics, which is the trace of this e to the beta h. Okay, so in general, this Hamiltonian is a matrix, right, in quantum mechanics, and we take this Boltzmann weight e to the minus beta h, and we take a trace of this operator, and we sum over all these possible eigenstates, we get this partition function. Okay, so any observables that can be measured in the laboratory is the expectation value of any operator A is actually computed by the standard quantum statistical mechanics. Namely, we multiply this density operator by this any quantity that we want to measure as an operator A, and we take a trace of this rho times A, which is summing over all these eigenstates, rho A, and this is nothing but the standard definition in your quantum statistical mechanics, which is the ensemble average of an operator, and you actually sandwich this by this eigenstate and sum over all this eigenstate, and inside the summation it is the this kind of Boltzmann weighting operator e to the minus beta h multiplied by this operator A and divided by this partition function, and this is the thermal averaging of a many-body operator at finite temperature. Okay, suppose we know all the eigenvalues and eigenstates, and this is what we should do in order to take the expectation value of a quantum mechanical operator corresponding to the many-body solid-state material, and we could just rewrite this summation in terms of this eigenvalues and this expression value inside the summation, and we could furthermore just rewrite this in a more familiar form that you should recognize this. In the numerator, we get a Boltzmann weighting factor e to the minus beta En, where En is eigenvalue, eigenenergy, multiplied by the matrix element, which is the expression value of this operator A sandwiched by this eigenstate, psi n, and divided by this partition function, which is nothing but sum over this Boltzmann weight e to the minus beta En, where En is eigenenergy. Right, so this is the familiar form when you do this thermal averaging of a many-body quantum system. So remember, when we talk about this ensemble average, this is what we mean. Of course, for a simple system like spin 1/2, it is possible to actually compute this thing. But for electrons and ions, it is almost impossible to find all these eigenstates and eigenenergies. And therefore, we need a way to actually count the quantized excitations. Okay, but the conditions that we know, some ground state wave functions or ground state energies. In a simple case like free electron gas, non-interacting, electrons in the metals, we are able to find out the ground state. For ordinary metals, suppose we neglected Coulomb interactions. And then we could build on the excited states based on this ground state that we know, and we could actually introduce the way to count this excited state electrons one by one, or excited states phonons, and so on. Okay, so this is a strategy. So we know something. The very simple limiting case And then we start to count these quasi-particles one by one based on this non-zero temperature ground state wave functions. And therefore, in some sense, we avoid doing this kind of troublesome summation, which we have no idea what they are. Okay, let's start the review of an introductory solid state. As you already learned, this lattice structure or crystal structure of solid state materials, that all the ions are orderly placed on this periodic lattice points, and we can define this unit vectors for this unit cell in real space, and we know that the electron number density n of r is also a periodic function in R. So that's the nature of a solid state, because all atoms, ions are crystallized and electrons are localized around that lattice point. Okay, so you'll see some modulations, periodic modulations of electron density over entire space. So that the electron density at any vector R is the same as R plus T, where T is a lattice translation vector, which is the linear combination of the three unit vectors of a unit cell, right? So this is well known. So the electron density is actually a periodic functions, okay? And we could also define the reciprocal lattice vector, which is reciprocal to the real space lattice vector. G, the reciprocal lattice vector G is defined by a linear combinations of all the three unit reciprocal lattice vector B, B1, B2, and B3, where B1, B2, and B3 are defined by this cross product between any two of this lattice unit vector. And this prefactor V1, 2, and 3 are all integers. So this is just a solid state 1, a very few pages of any introductory level of a solid state physics, and I hope everyone is familiar with that. I don't need to repeat these things. And the important properties of this reciprocal lattice vector, unit vector, is that when you make the dot product between this BI, our reciprocal unit vector, and the this AJ, where A is the unit vector in this real space lattice, and you get 2 pi times delta ij. This is 1 if I is equal to j, and 0 if I is not equal to j. So there's some sort of a orthogonal normalization between the real space lattice vector and the reciprocal lattice vector. So you could actually Fourier decompose this electron density function n of r in this expansion in terms of this Fourier space or reciprocal lattice space, where you sum over all possible g, where g is your reciprocal lattice vector, and inside the summation, this is the Fourier component of your electron density in a reciprocal space or momentum space, and this is a Fourier coefficient. You can make inverse Fourier transformations from this real space electron density to the reciprocal space. So there is an important relation that from the X-ray diffraction is that you could see this lattice structure if you do the X-ray diffraction experiments. And the idea is that you send this X-ray and you hit this target material, and the X-ray will get diffracted, and this is an elastic scattering, meaning there's no energy dissipation, and the magnitude of this incoming momentum of the X-ray is actually the same as the outgoing electron, the X-ray momentum, K prime, and the only difference is that the direction changes from K to K prime, where you can see this, there's a diffracted angle. And then you could use that X-ray diffraction to really see this lattice structure. And the idea is that you collect all this scattered X-ray particles, and you could actually get this patterns from this detector in this outgoing region, that this wave function as a plane wave of the outgoing particles is actually given by this type of scattering amplitude, where you sum over all this volumes, and inside the summation, it is the electron density in real space distribution multiplied by this phase difference between these two incoming and outgoing X-ray particles. All right, so if K and K prime satisfy certain relations, then you do get a bright peak from this X-ray diffraction pattern, so that you could really observe such periodic structures of ions. And if this K and K prime do not obey certain relations, then you don't see any bright peaks. So you see just a dark region. So that from this experiments, you could recognize and you could really observe the lattice points. So you could rewrite this outgoing wave functions in the following form, so that you will see this Bragg diffraction conditions. So this is I G minus delta K dotted R, where you can define this K minus K prime as delta K. So you immediately see that this is going to be volume times Ng. Suppose delta K is actually G. So this is the sinusoidal plane wave-like factor. So suppose reciprocal lattice factor G is not the same as delta K, then this sinusoidal wave is going to get cancellations once we sum over all the volume, so you get nothing. So you get something only if this delta K exactly the same value as G. This is the X-ray diffraction condition that you do see something if this condition is satisfied. And if you could expand this condition, you get what? Delta K is K minus K prime. If you square this, you get this condition, and you can simplify this since K magnitude is the same as K prime magnitude. So you get 2 times K dot G is G squared. Or in other words, to satisfy this K vector has to be half of this reciprocal lattice vector G. All right, so whenever you satisfy this condition, you will see the bright peak coming from the X-ray diffraction. If not, then you'll see nothing. And this condition turns out to be important to determine so-called the Brillouin zone. So the Brillouin zone is the zone in K vector where this condition is satisfied. So let me just review this Brillouin zone. The definition of this Brillouin zone is all possible value of K such that this K value satisfies this Bragg diffraction condition. Okay, so let me see if I have space. So once we derive this X-ray diffraction condition, we could define the Brillouin zone in K space, as we will repeatedly use this concept of Brillouin zone for later purposes. And you know very well how to define this first and the second Brillouin zone. So any questions so far? No? This is just a very boring review. But very soon you will not get bored, because something interesting coming out is that we consider a square lattice, and we defined the Brillouin zone. Okay, so a Brillouin zone is defined by this perpendicular bisector of the reciprocal lattice vector G. For example, this first Brillouin zone is defined by this blue lines, where all these blue lines are this bisector, a vector of this G1 and G2 and so on. This is G1 and this is G2, and this is in momentum space. So if you simply just bisect the the G1 and G2, and you form the square. This blue square is your first Brillouin zone. And if you go on to bisect the next nearest neighbor, a reciprocal lattice vector, and you'll get, say, the orange diamond Brillouin zone, which is the second Brillouin zone, and so on and so forth. So you should be familiar with that. And that's this lattice structure and this reciprocal lattice vector and so on. Any questions? It's just chapter 0 of your introductory level of solid state. But now here comes some non-trivial stuff. As I mentioned, we are dealing with two types of particles, namely fermions and bosons. So the definition of fermions that just carry half integer spin, and the bosons carry integer spin. And the examples of fermions are electrons and holes and positrons. And examples of bosons are light, photons, and phonons and magnons. And we know very well that this fermion satisfies Fermi-Dirac distribution, and they obey Pauli exclusion principle that no two electrons can occupy the same quantum state. But bosons shows Bose-Einstein distribution statistics, and also they like to get together at ground state, so we have a Bose-Einstein condensation phenomena. So for fermions, we have a Pauli principle, and we also have Fermi-Dirac distribution statistics. And for bosons, we have BEC, we have a Bose-Einstein statistics. So that's the elementary statistical mechanics that everyone should be familiar with. And so the homework number 1 is to ask you to review the Fermi-Dirac statistics from your quantum statistical mechanics, that you should derive the Fermi-Dirac distribution. For a number of fermions, occupation is given by this factor, where beta 1 over kBt, epsilon is the energy of your fermions, and mu is your chemical potential. And everyone should be familiar with this plot, that this occupation for fermions satisfies this Fermi-Dirac distribution, where this is the Fermi-Dirac distribution. You get full occupation of your fermions if they are within this Fermi energy, epsilon f, and completely empty if the energy exceeds this Fermi energy. And so you get a full occupation, meaning the state is completely filled with occupation being 1. There's 1 electron in a particular energy level if this energy is below the Fermi energy. If this energy is above the Fermi energy, and no electrons could occupy in that empty state, this is at 0 temperature. And at finite temperature, you get a smooth crossover from fully occupied state to fully empty state. Okay, so that sum of electrons could actually go to the excited states above this Fermi energy, and leaving behind some holes below the Fermi energy. So this is the free electron statistics, and I ask all of you to review and to rederive this by checking your quantum statistical mechanics textbooks. homework number 2, you should be able to derive the Bose statistics, the Bose-Einstein distribution function. But of course, you don't need to derive, this BEC phenomena, which will be covered in class. But these two different quantum statistics is a must-know knowledge. So you must know this right now, right here. Okay? And you must be able to derive such distribution functions for fermions and for bosons, respectively, from quantum statistical mechanics. Okay? So, in short, what we are dealing with in this course is nothing but a bunch of fermions and a bunch of bosons, and also couplings between bosons and fermions. So the basic knowledge for bosons and fermions is necessary. So this is something you should know by now. If you get familiarized with this derivation and you learn something, great. And let's just talk about these fermions and bosons. First, let's talk about the fermions. As we already pointed out in the introductory Hamiltonian, that if we look at the free electron kinetic energy plus the Coulomb potential, and you can understand most of these metallic properties, right? But here, we not only consider this free electrons, but also periodic potentials of electrons and ions. Then you will see that if we don't look at these periodic electron-ion potentials, you could derive these Fermi surfaces. Okay, and by including these periodic potentials between electron and ions, you will be able to derive energy bands. So this is a cartoon pictures of a one-dimensional periodic arrays of ions, and you know that the electrons are scattering around these ions, but electron and ions are attractive to each other, so they form very deep attractive potentials, very negative electron-ion potentials. But we know that ions are periodically are placed in this real space on the lattice points. In other words, this electron-ion potential is also a periodic function in space, right? So this is the shape of this periodic potential between electron ions, which attract this ion to pin these ions in this equilibrium position. So that's what it means here. So we should have a very simple analysis on this diagram and this cartoon pictures. This picture will lead to two things. First, without periodic potentials, we get Fermi surface, which means that this is made of more or less free electron gas. And in the presence of periodic potentials, we get energy bands like this. This is the, electron kinetic energy as a function of momentum k. And in the presence of the periodic electron-ion potentials, there's a band gap opening when this, electrons are fully occupy this lower band, and between this lower and upper bands, there is an energy gap, and this gap is proportional to this strength of potential U. And we will try to derive such a band structure. But before that, we should derive such a Fermi surface of many free electron system in the metal. So this is something that many of you should have known, but maybe some of you are not familiar with this Fermi surface, and you try to get familiarized. So let me just try to review this Fermi surface. So the Fermi surface this contour in momentum space with constant energy, which is given by the chemical potential of your electron. For example, if we are talking about a free electron gas, meaning suppose the electrons are scattering around without any lattice structure. Of course, the real case is not the same, but let's assume that we have such a nearly free electron, uniformly distributed in space, and those electrons satisfy the Schrödinger equation and that simple case can be solved by solving for the Schrödinger equation for electron gas, free electron gas. Okay? And that is easy. And that has been done. And everyone should have known this. Okay, so we will try to repeat the simple Schrödinger equation for free electron gas in just a moment. But let me just sketch what we have in this case is a sphere in momentum space where inside the sphere we have electron states, fully occupied electron states. Okay, all those yellow dots represent the electron states in K space where there is one electron per state, per dot. And this Fermi sphere is defined by the geometry where you exhaust all this electron in your system. All the electrons that are fully occupied are already populated inside the Fermi spheres, and leaving behind the geometry, which is a spherical shape, looks like this, and that is our Fermi surface for free electron in 3 dimensions. Okay, so the physical meaning is that around the surface of this Fermi sphere, electrons having the same energy, which we call this Fermi energy. So I will derive such geometry in just a moment, and in different cases we have different shapes of the Fermi surface. For example, on the lattice, where the electrons are tightly bound, called tight binding electrons on the lattice, and the Fermi surface shows a diamond shape, not a circle or sphere. But here is the simplest case where we have non-interacting free electrons. The contour in K space with constant energy is a sphere. We call it Fermi spheres. And all the electrons within the Fermi spheres are occupied at 0 temperature, and electrons are not occupying the other states out of the Fermi sphere, and which are completely empty, okay, at 0 temperature. But at some finite temperatures, some electrons below the Fermi surface can actually get excited and escape from those Fermi spheres and can actually go to the excited states. Okay? For example, suppose at finite temperatures, the electrons whose energies are very close to the Fermi surface could actually get excited like this. So this electron within the thin shells of this Fermi sphere at finite temperatures can actually escape from this Fermi sphere, and it get excited to the states that are above the Fermi energy. Okay, so that there is one excited state electrons out of the Fermi surface, but leaving behind a hole within the Fermi surface. And this is something that we are interested in studying. And this is called elementary excitations in metals. And later we will see that this kind of a so-called particle-hole pairs consists the low temperature properties of metals, where you only need to count how many such excited state electrons are there in your system, and then you will note their low energy properties or low temperature properties of this material. Okay, so when we introduce the second quantization, what we really mean is to not only count the number of occupied electron, okay? But also a number of excited state electrons. At very low temperatures, only very few electrons can actually get out of the Fermi surface and become excited state electrons. And that very few electrons could be counted in a systematic way so that all the thermodynamic and electrical properties are determined by those so-called quasi-particles. Okay? So this naive-looking geometry has a profound physical meaning, because at low temperatures we can't have such particle-hole pairs, and these determines all the thermodynamic properties of ordinary metals at low temperatures. Okay, so this is just a starting point, which things becomes non-trivial. So we will come back to these pictures once more at a later point, but this is just a review of your introductory level of a solid state for free electron gas in 3D, where this Fermi sphere is there. So in the remaining time, so I will give you a very short review of this Fermi sphere for free electron, so-called somofare non-interacting electron gas. So I believe most of you already heard about this, but it's useful to review it one more time. Great. As I mentioned, in a very simple limit, such as non-interacting electron gas, we could really solve the Schrödinger equation for many free electrons in a gas and find the eigenvalues and define the Fermi surface and so on. Okay, so that is really simple. Example, suppose we are dealing with a bunch of free electrons and with no potential energy, just a bunch of kinetic energy. That's it. So there are many, many electrons like this with only kinetic energy. So it is very easy to solve this Schrödinger equations, because we know very well in quantum mechanics, suppose this is just a free electron in one dimension, and we know very well from your undergraduate quantum mechanics that we could imagine that electrons or some particles live inside the potential well in 1D, and that is infinitely deep potential well, so that we have a boundary conditions that this wave function of the quantum particle vanishes at the boundaries, right? So you get a bunch of eigenstates like this. So we could very easily quantize the particle energies by solving for the say Schrödinger equation for such particles, and subject to the boundary conditions. Okay, so everyone should be familiar with this, and the solution is the sinusoidal function, and where Kn is 2 pi n by L, which is quantized, and it's integer value, and so you get this quantized energy levels, and you know the eigen function, you know the eigenvalue, you know everything. So this is just quantum physics, but let's just extend this to 3 dimensions. And again, we have a bunch of free electrons, living inside a box, a 3-dimensional box. And again, there are not just one electrons, like in this quantum physics. We have many, many electrons, but each of electrons satisfy the same Schrödinger equations without Coulomb interaction. So, you get a bunch of almost n copies of the same Schrödinger equations, right? So, in this case, the Schrödinger equation now becomes this. So remember, each of the eigenfunctions psi of k is a function of space as well. You got a bunch of independent free electrons which satisfy the same type of Schrödinger equations. for non-interacting particles, and you get the same boundary conditions, right? But now you simply just generalize this to three-dimensional eigenfunctions. And you can show that the product of the three sign functions in kx, ky, and kz coordinate indeed satisfy this Schrödinger equations for non-interacting electrons. And this energy, kinetic energy, is simply just the sum of this kinetic energy along the three directions, ks, ky, and kz. And you remember, this is really a sphere. If we fix this kinetic energy, so then you could imagine that in the three-dimensional space, in ks, ky, kz, the constant energy contour is nothing but a sphere, right? Let me just stop here, and we can continue next time. So you can imagine that this, on the surface of the sphere, the kinetic energy of the electrons show the same value, right? Okay. So, but you have a bunch of, states within this sphere where their eigenfunctions are described by exactly the same form of this eigenfunction. Okay, and then you could fill up all these free electron energy levels until you exhaust all your electron, and the final surface or sphere is your Fermi surface. So we stop here for now, and we'll continue next time. And we start from the free electron somewhere gas, and we know their eigenvalues and eigenstates and Fermi surface, and we will define density of states and all other observables next time. Okay, again, this is just a review of your introduction to solid state. Please go back to Kittel first book and review all this stuff that I mentioned today. And please also start to do your homework by going back to your statistical mechanics, quantum statistical mechanics, and understand the Fermi-Dirac and Bose-Einstein standard distribution. So far, so good, right? Everything is just very simple, elementary, but next week you will find something really non-trivial, really non-easy, and which may be beyond your understanding so far. Okay, so take the challenge, and remember to come to the class every time, and I'll see you on next Monday.